In this video, we're going to look at how we calculate pH of strong acids, and we'll also consider the ionic product of water. So strong acid, they are completely dissociated in solution. So strong acids will be the typical acids that you've come across so far. Hydrochloric and sulfuric acids are both strong acids. So when you dissolve them in water, they fully dissociate into their ions. Now, a number of protons released will depend on the type of acid. So if they're a monoprotic acid, like HCl or nitric acid or ethanoic acid, they release one H plus ion per molecule. Then sulfuric acid would be an example of a diprotic acid that releases two H plus ions per molecule. And then finally, a triprotic acid is something like phosphoric acid that has three H plus ions per molecule. So let's look at the pH scale. So the pH is defined as minus log to the base 10 of the concentration of hydrogen ions in solution. Why do we need to use a logarithmic scale? Well, those are our pH values that go from 0 to 14, and these are the concentrations of hydrogen ions that they represent. So a pH of 0 means we have a concentration of H plus of 1 mole per decimeter cubed, and a pH of 14 means our hydrogen ion concentration is 1 times 10 to the minus 14. So it allows us to represent a vast number of hydrogen ion concentrations on a simple scale of 0 to 14. So how do we work pH out? So here's some examples where you've got a solution of hydrochloric acid. Concentration is 0.2 moles per decimeter cubed. What's its pH? Well, for HCl, it's a monoprotic acid, so the concentration of H plus will be 0.2 moles per decimeter cubed. Then we pop that into our pH equation and to give us a pH of 0.70. Nitric acid, now with a pH, so we're going to look at the concentration. They've given us the pH of a solution of nitric acid. So we now can change our pH equation around to the concentration of H plus is 10 to the minus of the pH. So that's 10 to the minus 1.1. And that gives us a concentration of H plus ions as so. And because it's a monoprotic acid again, that's the same as our concentration of nitric acid. So question 3, we're going to find the mass of phosphoric acid required to make up a 250 centimeters cube solution of pH 2.35. So first of all, we work out our concentration of H plus from the pH, and then we need to divide that by 3 to find our concentration of phosphoric acid, because that's a triprotic acid. Having done that, we find our moles of phosphoric acid in 250 centimeters cubed by multiplying our concentration by 0.25, because we've converted 250 centimeters cubed into 0.25 decimeters cubed, to give us the number of moles. And then finally, we multiply that number by the molar mass of phosphoric acid, which is 98, to give us our mass of 3.65 grams. So question 4 then, we're going to calculate the pH of a solution when we've added 100 centimeters cubed of water to a 50 centimeters cubed solution of 0.1 moles per decimeter cubed nitric acid. So first of all, the concentration of H plus in the original solution is 0.1 moles per decimeter cubed. So in our diluted solution, it's going to be that concentration times the old volume divided by the new volume, which is, of course, 50 divided by 150. That gives us 0.0333, and therefore, to find the pH, we just do minus log 0.0333 to give us a pH of 1.47. And number 5, we've now got a pH of a solution formed when we've got 250 centimeters cubed of 0.3 sulfuric acid, and we're making it up to 1,000 centimeters cubed with water. So again, we find the concentration of H plus in the original solution, and we need to times our concentration of sulfuric acid by 2, because sulfuric acid is a diprotic acid. Then we do the same of multiplying by the old volume dividing by the new volume, and we get 0.150 for that. And then we take the log of that number to give us a pH of 0.82. So in water, a tiny proportion of our water molecules are dissociated, and we call this the ionic product of water. So we can look at the equilibrium for that of a water molecule dissociating into an H plus ion and a hydroxide ion. And because we have an equilibrium, we can calculate Kc for that. But of course, the concentration of water is so much larger than H plus concentration, OH minus concentration, that it's effectively a constant number. It changes so insignificantly. So we can rearrange that to give us Kc multiplied by H2O. The concentration of H2O is equal to concentration of H plus times concentration of OH minus. And we just combine those two into Kw. And we can define a new equilibrium constant, Kw, as the ionic product of water as being equal to the concentration of H plus times the concentration of OH minus. And in pure water, we can use that to work out the pH. In pure water, the concentration of H plus is equal to OH minus. And so Kw is equal to H plus squared. The numerical value of Kw is 1 times 10 to the minus 14. So if we substitute that into the equation, the concentration of H plus is 1 times 10 to the minus 7. And when we find the pH of that, the pH is equal to 7. Now this equilibrium is endothermic. So if we increase the temperature, the equilibrium will shift in the endothermic direction, which is towards the products. So both the concentration of H plus and OH minus will increase, and that causes Kw to increase and our pH to decrease. But it's really important to note that just because the pH will no longer be 7, the water is still neutral because H plus is still equal to the concentration of OH minus.